Hello students, welcome to EPG Pathshala. I am Dr. Ayushi Paliwal from University of Delhi. Today we are going to discuss about the module Standing Wave Propagation in a Transmission Line from the paper Electronics. So students, let us see what we are going to learn in this module. First, we will discuss about the wave propagation in lines. Secondly, the standing waves for different loads will be discussed. Thirdly, relation between standing wave ratio and reflection coefficient will be discussed. Lastly, we will also discuss about the effect on standing wave ratio and input impedance considering the special cases of load impedances. So let us start with the basic introduction about the module. When a wave travels on a transmission line and finds an impedance mismatch, partly or all of it's reflected back in the opposite direction. This is typically what happens when a cable is connected to an antenna. If the antenna impedance does not perfectly matches the line impedance, a reflection takes place and some of the power that the transmitter is sending to the antenna is reflected back. So a generator is delivering power to the load through a transmission line. If the impedance of the line does not match the impedance of the load, a reflection takes place and some of its power is reflected back. When both forward and reflected wave travel simultaneously in the opposite direction on a transmission line, the resulting wave being the superposition of the two waves is called as the standing wave. Having standing waves on a transmission line is not necessarily a bad thing, but transmitters usually do not like receiving back part of the power they deliver. So to keep this phenomenon under control, many tools exist like impedance meters, impedance bridges, network analyzers, SWR meters, reflectometers, and so on. But they don't always quantify it in the same way. So the goal of this calculator is to easily convert from the different ways of quantifying the reflected waves. Wave propagation on lines. Consider a matched line that is a case of no reflection. A sinusoidal wave is applied to the one end through source resistance Rg equal to Z0. The signal would move down the line and disappears into the load or the traveling wave. This process would take time. Once the sine wave has been operating long enough for the initial part of the signal to reach the far end of the line, a steady state situation will exist. So the signal at any point along the line will then be the same as that at the source, except for a time delay. This time delay is the phase shift for a sine wave. A time delay of one period, that is a phase shift of 360 degree, or one complete cycle resulting in delay in a wave is indistinguishable from one that has not been delayed at all. So the phase of the incident wave increases with increase in Z in the line. The length of the line L that causes a delay of one period 2 pi is known as a wavelength lambda, and the voltage along the line at one instant of the time is like input sine wave with x-axis as the distance, and the propagation velocity is given by Vp equal to lambda by t and Vp equal to f lambda, where t is the time period, f is the frequency. Since lambda gives a phase shift of 360 degree 2 pi, phi equal to 2 pi L by lambda, where phi is the phase shift due to the line of length capital L. Thus, transmission lines can also be used to introduce the phase shifts and time delays deliberately when required. So students, let us now discuss about the standing waves. There are two cases with matched line, that is, we have the identical sine wave at every point on the line as the incident wave travels down it except for the phase. Second is if the line is unmatched, that is, the reflected wave from the load is also expected, which add to the incident wave from the source. So consider a simple case. We have the unmatched line of length L equal to lambda, that is the open circuit line. The reflected voltage has the same amplitude and polarity as that of the incident voltage at the load, and chosen to match the line at the source. So if there is a mismatch at the two ends, L not equal to lambda, situation will be complicated by multiple reflections. So at every point of the line, the instantaneous values of incident and reflected voltage add algebraically to give the total voltage at every point on the line varies sinusoidally, but the amplitude of voltage varies gradually due to constructive and destructive interference between the incident and the reflected waves. So there are a series of locations where two sinusoids are in phase and another series of locations where they are out of phase, phi equal to pi. Where they are in phase, they add directly at each instant, that is, total voltage has maximum amplitude, and where they are out of phase, they subtract. So the interaction between the incident and the reflected waves resulting in the stationary pattern of the waves on the line. Standing wave patterns for three types of the load. So this figure shows the various standing wave pattern. Now if ZL is greater than Z0, then the gamma R equal to ZL minus Z0 divided by ZL plus Z0 is greater than 0, which means that the incident and the reflected waves are in phase at the load. Now when the reflected light is present but has lower amplitude than the incident wave, then the standing waves of current and voltages are present, but no point on the line where voltage or current remains zero over the cycle, as shown in this figure. So we have the voltage standing wave ratio VSWR or SWR equal to Vmax by Vmin greater than equal to 1. So SWR concerns magnitude only. For matched line, SWR is equal to 1 as no reflected wave and no interference, that is Vmax equal to Vmin. So close the line to matched lower the value of SWR. Both SWR and gamma R measures the amount of reflection on a line. Let us now discuss the relation between SWR, standing wave ratio, and reflection coefficient gamma R. Consider a lossless line. So the maximum voltage on the line occurs when the incident and the reflected signals are in phase. That is Vmax equal to VO plus VO minus, where VO plus is due to the incident signal and VO minus is due to the reflected signal. Similarly, minimum voltage on the line across when both are out of phase, that is they are at lambda by 4 away from the maximum, then V minimum equal to VO plus the modulus of it minus the modulus of VO minus. So therefore the standing wave ratio SWR is Vmax by Vmin equal to the ratio of VO plus VO minus divided by VO plus minus VO minus. So SWR will be equal to the ratio, that is SWR will be equal to 1 plus the modulus of gamma R divided by 1 minus the modulus of gamma R. So for a lossless line, this modulus of gamma R equal to the modulus of V0 minus by V0 plus multiplied by exponential 2 pi beta L. That is multiplied by exponential j. So the inverse relation is S minus 1 equal to modulus of gamma R multiplied by S plus 1. So gamma R, the modulus of it will be equal to S minus 1 divided by S plus 1. So for special case of a lossless line terminated in a resistive impedance, the relationship between SWR, that is S, load and line impedance is S equal to 1 plus modulus of gamma R divided by 1 minus modulus of gamma R. So let us now discuss the case 1. If ZL is greater than Z0, S equal to 1 plus ZL minus Z0 divided by ZL plus Z0. This whole divided by 1 minus ZL minus Z0 by ZL plus Z0. So S equal to ZL by Z0 greater than equal to 1. And the case 2 is Z0 is greater than ZL. We have S equal to 1 plus Z0 minus ZL divided by ZL plus Z0 divided by 1 minus Z0 minus ZL divided by ZL plus Z0. So your S is equal to Z0 by ZL greater than 1. And your Imax is equal to Vmax by Z0 equal to V0 plus V0 minus divided by Z0. And Imin is Vmin by Z0 equal to V0 plus minus V0 minus divided by Z0. Reflection causes the power dissipation in the load to be less than it would be with a matched line for the same source, as some of the power is reflected back to the source. Since power is directly proportional to the square of the voltage, which results in the fraction of power where that is reflected and is equal to the square of the voltage reflection coefficient. So therefore, PR equal to gamma R square multiplied by PI, where PR is the power reflected from the load, PI is the incident power at the load, gamma R is the voltage reflection coefficient, gamma R square is the power reflection coefficient. So the amount of power absorbed by the load is PL equal to PI minus PR. So PL equal to PI multiplied by 1 minus gamma R square, where incident power is Pi, that is V naught plus modulus the whole square divided by 2 Z naught, and the negative sign in the average power, that is P average, is 1 by 2 real VSL multiplied by IS star L, and the negative sign in the reflected part is due to the negative going wave as the reference direction is traveling towards the right. So the power PL from the above equation, it is constant for a lossless line and does not depend on L. Also the maximum power delivered to the load when gamma R equal to 0. Since SWR is easy to measure, so equation J can be modified and it is PL equal to 1 minus gamma R square modified to PL equal to PI multiplied by 1 minus S minus 1 divided by S plus 1 to the power 2. And PL is equal to PI multiplied by 4S by S plus 1 to the power 2. So reflections on transmission lines can cause problems in receiving applications as well. Reflections on a TV antenna feed line can cause a double image or ghost to appear. In transmission, reflections can distort pulses, causing errors. So let us now discuss the two special cases. The first case is that of a shorted line, ZL equal to 0. Now here, the value of the input impedance Zn becomes Zn equal to Z0 multiplied by ZL plus Z0 tan hyperbolic of gamma L divided by ZL tan hyperbolic of gamma L plus Z0. So for a lossless line, gamma equal to J beta and alpha equal to 0. Therefore, Zn equal to Z0 multiplied by ZL plus JZ0 tan hyperbolic of beta L divided by JZL tan hyperbolic of beta L plus Z0. This is marked as equation L. So equation L becomes ZSC equal to Zn at ZL equal to 0. So ZSC becomes JZ0 tan of beta L. Also gamma R equal to ZL minus Z0 divided by ZL plus Z0 equal to 1 for ZL equal to 0, and S equal to Z0 by ZL equal to infinity as Z0 greater than ZL. So here Zn is pure reactance, which is represented by equation M and could be C or L depending on the value of line length L. Now it should be noted over here that though a section of transmission line terminating in an open or short circuit is useless for transmitting the power but can serve other purpose. Such a line can be used as an inductive or capacitive reactance or even as a resonant circuit. So in practice, short-circuited sections are most common as open circuit lines tend to radiate energy from the open end. Thus, ZSC has no resistive component and hence dissipate no power. So for short length less than lambda by 4 or 90 degree, ZSC equal to inductive. At beta L equal to pi by 2, the line looks like the open circuit. So for pi by 2 less than beta L less than pi, the line is capacitive as tan of beta L is less than 0. For beta L equal to pi, line behaves as a short circuit as tan of beta L equal to 0, which is shown in this figure, and for longer lines, the cycle repeats as shown in this figure for beta L greater than 180 degree. Now at beta L equal to pi by 2, the line behaves as a parallel resonant circuit, that is, it has a very high impedance. At beta L equal to pi, line behaves as a series resonant circuit and has very low impedance. Let us now discuss the another case, that is the open circuited line ZL equal to infinity. So now here equation L becomes ZOC equal to limit ZL tends to infinity Zn equal to Z0 by J tan of beta L equal to minus J Z0 cot of beta L. Also, gamma R equal to ZL minus Z0 by ZL plus Z0 equal to 1 for ZL equal to infinity. So, Zs equal to Z0 by ZL equal to infinity as ZL is greater than Z, the Z0. So, from equation M and O, we have ZSC multiplied by ZOC equal to Z0 square. So, now as shown in this figure, if we have beta L less than pi by 2, line is capacitive. At beta L equal to pi by 2, line is short circuit, and it's the case of series resonance. For pi by 2 less than beta L less than pi, line is inductive, and for beta L equal to pi, it becomes the parallel resonant circuit or the open circuit. Now the last case is a matched line, that is when ZL equal to Z0. It is a most desired case, so equation L becomes Zn equal to Z0. So gamma R is equal to ZL minus Z0 by ZL plus Z0 equal to 0. So S equal to Z0 by ZL equal to 1. This implies that V0 minus equal to 0, that is entire wave is transmitted and there is no reflection. So incident power is fully absorbed by the load. Thus maximum power transfer is possible when a transmission line is matched to the load. Because of the negative sign appearing in the current equation, equation 11 and 12, it is evident that at the positions on the line where the two travelling wave terms add in the voltage resulting in Vmax, they subtract in the current relation giving Imin and vice versa. So the maximum voltage position in the line is then a minimum current position. So because of recalling the equation 30 for lossless condition, we have gamma equal to J beta, alpha equal to 0. So the input impedance, that is Zn of the line, varies periodically with electrical length beta, that is period. So Zn, the maximum value of it will be Vmax by Imin equal to Z0 multiplied by modulus of V0 plus V0 minus the modulus divided by modulus of V0 plus minus modulus of V0 minus equal to Z0 S. So at position where Vmin occur, current is maximum, giving minimum and real impedance. So in this case, Zin minimum will be equal to Vmin by Imax. So this is equal to Z0 V0 plus V0 minus divided by V0 plus V0 minus equal to Z0 by S. That is the reciprocal of it. So in transmitting applications, standing waves part additional stress on the line and can result in failure of the line or of equipment connected to it. So the transmitter connected at or near a Vmax output circuit of transmitter may subjected to overload condition. This may damage solid state transmitter. Thus needed circuit to reduce output power is the presence of a signal to noise ratio, that is, say standing wave ratio greater than 2. So students, let us summarize what we have learnt in this module. First, we learnt how the wave propagates in lines. Secondly, we discussed about the standing waves for different loads. Thirdly, the relation between standing wave ratio and reflection coefficient was derived. Lastly, we also discussed the effect on the standing wave ratio and the input impedance of the special cases of load impedances. Thank you.